This video was produced by
Well, welcome to the Institute of Visual Studies. I'm Daniel Robinson, the Assistant Director of IVS. I feel like most of you have probably been here before, but IVS is a multidisciplinary institute for, we work and deal with images primarily. We offer studio seminar classes, exhibitions, and colloquia, which you are in now. So, just to let you know, our next event is April 16th. There are students in this class in the current studio seminar that are busily preparing for this exhibition. So come back on April 16th from 11 to 1. The following day on the 17th will be our final colloquium of the semester. All right. Today we are very fortunate to have Dr. Laura Taalman here to give her colloquium. Laura has been at JMU since 2000 and has won numerous awards for her excellence in teaching. And most recently, she won the Outstanding Faculty Award from the State Council for Higher Education, which is very prestigious, and we're very, very lucky to have her.
Hi, so thank you, Daniel and David, for doing this great series of talks and for letting me be part of this one. I'm going to talk to you about spiral knots today, which is some work I've been doing with undergraduates, also with Len Van Wyk in the math department. But the talk is really going to be more about what it's like to do mathematics. What is it like to explore things in mathematics, and what does a mathematician do? So I want to start with an example of what you're looking at right here, which is a glider gun emitting some gliders. This is part of Conway's famous Game of Life, which is a game where you imagine a grid where the cells of the grid, the squares of the grid, are either on or off, alive or dead at any time step. And then as you step forward through time, the squares become alive and dead according to this set of rules right here. Now, that's a little complicated to deal with right now, so I'm going to deal with a much simpler set of rules and starting with just one dot. Okay? So if we start with one live cell, I'm going to use this simpler set of rules. And my set of rules is going to be that at any time, if a cell is already on, it's just going to stay on, right? Cells are never going to die. And cells that are off are going to turn on precisely when exactly one of their adjacent neighbors is on. Okay, so their left, right, north, south neighbor, if they have one of those that's on, they're going to turn on. So in the first step, we have one cell. And then we get 4, because that's how many cells had exactly one neighbor in that time step and they turned on. So how many will I have in the next time? How many will be added? It'll be like 1 here, right? 1 here. No, less than 9. Oh, there will be 9. I'm sorry. There will be 9 because we'll add 4, right? The 4 will be added. So how many will be added now? 12. That's right. 12 will be added. And now 4 again, right? It's not an increasing sequence that's of additions, at least, although the sequence itself is increasing. And now 12 again, and I think this is the one where there are a lot. No, just 12 again. Now there are a lot. How many are there now? Yeah, that's a good answer. Lots. So 36. That's good. And then, surprisingly, the next step is going to be 4. Okay, it's going to go back to being 4 again. So, okay, so you're a mathematician and you need a problem to work on, and you think, maybe I could investigate this sequence, right? Maybe I could come up with a rule that tells me at any time step how many lights will be on, or a rule equivalently that tells me at any time step how many lights will be added. So a quick way to do this is to go to the internet and just type in the sequence that you're interested in. This didn't exist in 2000 when I got here, but now you can just see if the internet knows about what you're thinking about already. And so you type this in and you say, Internet, do you know anything about this sequence? And this is the online Encyclopedia of Integer Sequences, this huge compendium of sequences known to have certain properties. Okay? Turns out this is a known sequence, and in fact it's exactly the rule that we were talking about cells turning on. They've computed it out to way more digits than we've computed it out to, right? So they've done a lot more work. And in fact, if you scroll down, you find a link to a website where you can get a research paper that actually answers the question completely. Okay, so here's an answer to the problem. It's a formula, tells you exactly how many cells turn on at any time step, and the proof. Now in math, when you don't want to talk about a proof, you just say it's clear. Okay? So the proof is clear. All right, so what just happened? We had a sequence. We thought maybe we could expand the frontiers of mathematics by researching this sequence. We want to know if there's a pattern. We look to see if anybody else might have thought of this sequence before. We don't want to reinvent the wheel. And they had. So someone else have already thought about it and actually solved the whole problem. So this is the absolute worst thing that can happen to you in mathematical research. It's interesting, right? Because we can learn about the answer. But we have no research here. There's nothing that we can publish here. So math is this game of finding interesting problems to solve that are actually tractable for you, or maybe even for some students who are working with you, and then hoping no one else proved it and proving something nobody else has ever proved before. So let me show you how that works in context of what I do, which is knot theory. So here are some knots. Knots are just circles that are all knotted up in space and then glued back together again. And the names next to them, these numbers are just their names. So like 8, 8 is the name of this knot right here. The big 8 refers to the fact that the knot has 8 crossings in its picture, and that's the least we could ever have in a picture for that knot. And the second 8 just means it's the 8th in the list. This is literally just a list, okay? So here's a whole bunch of knots. And in knot theory, we're interested in questions like, how can we tell if 2 of these knots are really secretly the same? Or how could we tell if 2 of these knots are actually different, can't be changed from one to the other? So I'm going to focus on one. I'm going to focus on, there we go, 6, 2. So here's 6, 2. 6, 2 has an interesting property that if you stretch it out and you pretend like the string is made of something very stretchy, you stretch it out, you move it all around, you can rearrange the knot and flatten it out again so that it looks like this, believe it or not. I know that doesn't look like it. Do you guys want to go over there? Because there's like seats right there. And I was at a talk once where I had to stand in the back. Yeah, go ahead. I'm sorry. OK. So anyway, we can make 6, 2 look like this. And in fact, if you look at the gray part, we don't really need that part, right? It's pretty clear that that's just attaching the ends to the ends. So I'm going to erase the gray part. And now I have a new representation of 6, 2. And in fact, I can make a little code out of this representation. So I'm going to use the code ABC capital D, ABC capital D. And the reason why is this. At each level, I'm going to record a letter if there's a twist at that level. And I'm going to record a lowercase letter if the overstrand is coming from the top, and an uppercase letter if the overstrand is coming from the bottom, like it is here. So this is the knot ABC capital D, ABC capital D. I could call you on the phone and say, I want to have a conversation with you about the knot ABC capital D, ABC capital D, and you will know exactly what I'm talking about, right? Which is not necessarily as easy to describe if I try to describe the blue picture. Okay? So I have this nice codification of the knot. So this is called a braid projection of the knot, and this is called a braid word for the knot. But in this particular knot, the word is very repetitive, right? It's just the same chunk repeated over and over again. That's what makes it a spiral knot. A spiral knot is something that will use all the letters in order with some capitalization, and then it'll repeat that chunk over and over again. So in spiral knot language, we call this S spiral, 5. There's 5 strands. 2, because the repeat happens twice, over, 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 under. Okay? So that's just fancy language for this particular spiral knot. So some questions should occur to you immediately. For example, do all knots have a braid projection? Is 6, 2 special? Or can I take any knot, stretch it out, and get it to look like this thing and have a code word that I can call you on the phone about? And the answer is yes. And we've known this for a very long time, almost 100 years, which in knot theory is a long time. So knot theory is a pretty young field, so 100 years is a long time. And so we've known that for a long time. So how about a spiral projection, right? One where we use ABCDD all in order, right? And then we repeat that chunk over and over again. Well, okay, so when mathematicians don't know the answer to the problem, they don't like to say that they don't know because it makes them sound dumb. So you say it's an open problem. So it's an open problem whether or not every knot has a spiral projection. We actually don't know that. Now you can get into more complicated questions, like a student and I worked on this problem last summer. Are spiral projections minimal? In 2 different senses, we proved that they are not. In one sense, you can see that the spiral one uses 8 crossings, and this is only a 6 crossing knot, so it's not minimal with respect to crossings. This one uses 5 strands, but there's actually a non-spiral braid projection that uses 3 strands for this knot, so it's also not minimal with respect to the number of strands. And what we proved is, in fact, this particular knot, there is no other spiral representation that would be minimal for this knot. Okay? So, and the proof of that is clear. Okay. So your math goes much faster when you do it this way, I have to say. It's really good. So okay, so here's our knot table again. And we are interested in knowing which of these are spiral knots. We already said we don't know if they're all spiral knots or not. And these ones highlighted in blue are what's known as Taurus knots. Those are the ones where the pattern is over the whole way down. This is a very well understood class of knots. Almost everything you would want to know about Taurus knots is known, and that's in fact why Len Van Wyk and I developed these spiral knots, because they're a natural extension of Taurus knots. We can take what's known for Taurus knots and hope that we can extend it to spiral knots. So we're not just, working in a void starting from nothing. We're starting from some known results and trying to expand those results to a larger class of knots. Now, at the time that Len Van Wyk and I first started thinking about these knots, this is how many knots we knew were spiral besides the Taurus ones. Oh, actually, it's just 2. I was going to say these 2 up here. And then since then, I actually have found with some students all these other spiral knots. And for all we know, all of these are spiral knots. We just don't know. So I could write down lots of them, lots of spiral knots, but I don't know which ones of these categories they belong to. So that's also an open problem. Okay. So let's take 2 of these spiral knots, the 2 that we actually have known about for a long time, 6-2 and 6-3. It turns out they're both spiral knots, and in fact they have the same number of strands and the same number of repeats, and they only differ in one of the crossings, right? So it's over, under versus over, under. Okay? It turns out that through a mysterious process that I don't want to talk about right now, but there's some process that can assign a number to a knot. Okay, so we go through this process, we start with a knot, we go through the process, we get a number. In this case, we get 13. In the second case, we get 11. 13 is not equal to 11. And it turns out that the way this mysterious process works, if these numbers aren't equal, then the knots can't be equal either. So if the numbers aren't equal, there's no way I can change one knot into the other. That's just part of the mysteriousness. You just have to trust me on that those won't be equal either. And that's what it means to be a knot invariant. It's some property that if you can show that the 2 knots differ on the property, then you know the 2 knots aren't the same. If we had determinant 13 for both times, we would not know that the knots are the same. But we do at least are able to distinguish knots with this property. Okay, so big question in knot theory is to compute the values of various invariants for certain classes of knots. So I want to talk about what the determinants of spiral knots are. So given all the spiral knots, maybe I can get a formula for all spiral knot determinants. So here's some data about spiral knot determinants. Some of this you can find this by hand if you want to, or you can use a computer to do like this. We have this table to much farther, right, which would be very tedious and involve some very large calculations. Some of the data in this table were already known because they were Taurus knots. So these are the over knots in these columns. This is 4-strand spiral knots, 5-strand Taurus knots, spiral knots, and K is the repeat. And then this is the pattern. Okay? So the Taurus knots were already known. There's a nice formula for those determinants, and we would really like to have a formula for all spiral knots. This here is something that we proved. Oh, it shows up well on that one. A result that we proved in our first paper about spiral knots had as a consequence that these rows have this weird modularity property. So the last row, for example, it says 1 mod 7. Every single one of these numbers is congruent to 1 mod 7. What that means is if you subtract 1 and you divide by 7, you get an integer. You subtract 1, it's still divisible by 7. So that's actually true of all those numbers, and it's a consequence of a result that we did a few years ago with some students. More recently, there's a pretty obvious pattern right here, right? It pretty obviously looks like we're going to have cubes going down here. And that was actually proved by a couple students last year using, I think I have it here, yes, Jordan canonical forms. So if anyone's teaching advanced linear algebra, this is actually useful, which is really great. But for everybody else, the proof is clear. Okay, so that's done. That technique actually doesn't work all the time. We thought it would work all the time, but for the mathematicians, brief note, the characteristic polynomial doesn't always split. And so then we get into trouble when we try to do that method for other knots. In fact, it splits very seldom, and everyone is quite upset about this fact. Okay, so, and yesterday we were working on this result. So yesterday we actually, last week we managed to prove a formula about this result. And then yesterday we were talking with Dr. Field about how to fix the recurrence relation that's in this result. So this is really cutting edge stuff that's going on right here. Now this is a weaving knot, over, under, over. And so let me look at, instead of all the possible patterns, let me look just at weaving knots, because that's where things get really nuts. Okay, so here's a table. It's just for weaving knots. You see the patterns are always alternating like that. These gaps in the patterns is where the knot would actually be a link. It would have two or more components that were put together instead of just one circle. And we're in the process of calculating these right now. But at the time when I made this table, we didn't actually know how to do that efficiently. So, but we're going to have this data later. But right now, so this is just for knots. These results are already known if you go forward. Strangely, there is a formula for this which turns out to be something called the Pell numbers. Now, if you know what Fibonacci numbers are, I know, that's what I said. I know. So the Fibonacci numbers is a nice sequence of numbers where each number is the sum of the two previous numbers. This is just each number is 2 times the previous number plus 1 times the number before that. So this is a very nice formula for this row. And it also can be written like that with some ugly square roots if you prefer that. Down here, this formula was also known by a student that started out at our JMU REU and ended up doing research at St. Mary's College of Maryland with another professor when she went back home to her school. And this uses the Fibonacci numbers, which is another relation like that. In fact, last year, one of my students showed you can simplify that horrible formula to something involving the Lucas numbers, which is also a kind of nice recurrence relation where you have the sum of the two previous things. It just starts from different place. So you can see these similar patterns everywhere, but we don't actually know what the whole pattern is. So there's the story that lots of people tell about mathematics is that it's like lots of blind men looking at an elephant, right? And so like one blind man is looking at the trunk, and another blind man is looking at the foot, and another blind man is looking at the tail, and then they're all, I don't know, talking on their walkie-talkies or something about the elephant, and trying to piece together what it is that they're looking at. But each one can only see a tiny piece. So this is like the foot of the elephant, the trunk of the elephant, and we're looking for the elephant. And maybe we'll find that elephant. So that can also be written in this crazy way with the roots. And the reason I say that is our Jordan form technique actually can find us a formula like this with the roots, which we just recently showed we can write as a recurrence relation. And then the n equals 6 case, things get a little bit hairy, and at this point we would like to find the elephant before we keep looking at any more tails, because this is just messy, right? We want to find what the general thing is. And n equals 5 is one of those bad cases I was talking about. Okay, so what happened here? We want the formula for the determinant of any spiral knot. Can we prove that? No, we don't know how to prove that. So we have no idea how to prove that. Oh, that doesn't really show up very well over there, but it says try again. So you can try again. But we can prove a whole lot of little things, okay? And each one of these little things is a good starting undergraduate research project for an undergraduate who wants to do some mathematical research. And when we finally put them all together and see the forest for the trees, we might be able to find the whole result. And it's even possible that all knots are spiral, which would mean that we have a different way for calculating the determinant of any knot. A very non-practical, useless way, I have to admit, but a way. Okay, so all the knots we've been dealing with are three-dimensional in the sense that my picture of it looked like a tube with a shadow and everything, right? But it's not really three-dimensional, it's really very flat. And the reason it's flat is because mathematicians who do knot theory like to label the strands and then do some kind of combinatorial magic on the strands to get the determinant and other things like that. So it just helps to have a flat picture. But if we wanted to, we could take that flat picture and tighten it up into something in 3 space, and that's exactly what Jason Cantarella at the University of Georgia did. He took all knots up to, I don't know, 10 crossings or something, a lot of knots, and used a gradient descent algorithm to make like these tight minimal knots, right? So this is sort of the smallest the knot can get in space. And he did that with some students, as a matter of fact, as well. Now, his data we can put into a nice, this is a free online CAD program, and if you look at the shadow, it actually looks like our friend 6'2", right? So that was 6'2", and the flat is just sort of projecting it down onto this particular plane. Now, the cool thing is, if we can put the data into a CAD program to look at it, it means we can make it. So anybody who's familiar with this room knows that there's a replicator 1 over there. That's where I printed the first knot for our project, which is going to be to print a 3D table of knots. So instead of the flat table, a 3D table. And the hope is that maybe there's some invariant out there that's easy to see when you're holding a 3D knot that somehow is missed by the flat projections, right? Maybe not, but if not, then at least we have a pretty collection of knots. So I have some knots to hand out to you here. I know how many there are, so wait, let me just double check. 2, 4, 6, 8, 10, 12. I don't trust you at all. 14, 16. Okay, so okay, fine. So you can just maybe take one and then pass the box along so other people can look at them and just sort of pass them all around. So these are examples of knots that have been 3D printed using the data from the University of Georgia. And while you're passing that out, I'll just explain briefly how these knots came to be. So up there you see the data put into a form that Mathematica can understand. It's actually quite a lot of data. It goes off the screen, but that's the end of it. Here, the data is actually just dots, but Mathematica is very easy to make it put tubes around the dots and connect everything up. And then you see I export it to a file that can be read by that nice online CAD program where we can put cute little labels on the knots so that we don't just have a whole bowl of squiggles to deal with when we print out. It took me printing 3 different knots to realize, wait a minute, I can't tell all of these knots apart. I'm going to have to put a label. Anyway, then you can get it into the software that runs the 3D printer, put it through the 3D printer. Here it is printing it. You can see the slice. It's printing it in slices. Here it is printed out with the support material that needs to be ripped off. And here it is after it's all cleaned up and the little numbers are painted, and that's what's being handed around. And that's all I have. Thank you. Question time. Yes?
I have a question. Sorry, I think I missed something
Okay.
kind of basic when you were talking about looking at determinants for different sizes of n.
Yes.
What was n? Was n the number?
Oh, n is the number of strands, and then k is the number of repeats.
Okay.
So in the first set of table, there was like n equals 4 and n equals 5 table. But then in the next table, it was like, I think there was both an n and a k in the table somewhere. But yeah, n is how many strands there are, and then k is the number of repeats. And then the plus minus is the over-under business that happens.
Okay.
Mm-hmm. Yeah.
Is determinant related to the basic determinant that I learned about in basic algebra?
It is. So what happens is, you know that picture where I was talking about how we label the strands and they were like colored strands? So you take these strands and you put certain algebraic labels on them and you make a matrix out of that. And then in the case of these spiral knots, because they're so repetitive, you end up just having to take powers of a small matrix. It's this new thing that we found works for spiral knots that doesn't work for other knots. And then you take the determinant of that, well, of a piece of that matrix. But yes, the actual determinant happens at one point in that process, and then it's called the determinant. Yeah.
So what did you mean when you said the characteristic polynomial doesn't exist?
Well, over R. And right now, I don't know how to deal with it over C in Mathematica, and if you know, then I want to know.
But it splits into quadratic factors, right? It doesn't split into...
Doesn't entirely, yeah. When I say split, I mean, yeah, yeah. Yeah, it's going to be everything would do that. Yeah.
Well, I was curious. I thought
Yeah,
you
yeah,
meant
yeah.
something else.
Yeah, no, just that. And I'm sure there's a way around it. I just like got stuck at my own limitation for a minute there, and then so now we're doing all the ones, so this is the easy case, and then we'll see, just do it over C or something. I'm sure it'll work out.
Factors, linear factors, and calculation.
It's at least possible because you know the matrix we need to take a matrix to a large power, which is why I want to use the JCF. That's the only reason I need the JCF is to get this matrix to a large power, and then eventually I have to multiply some pretty big matrices together, and then yeah. But most of it is that power. Yeah.
My question's about the publish or perish part, because I'm in art, and I'm just curious, what does it mean when an undergrad student does research with you then goes to another university, maybe is doing their PhD, and they then are continuing it, and or like the professor from Georgia, now you're using that model
Data, and their
to do
students
your work.
had that data.
So it seems like you have a real sharing of research, and
Yeah,
how does that
and I-
relate to the publish or perish?
Well, I don't know. To me, math is very open, and there is a lot of sharing, and then people publish what they have, and usually people develop results independently, but they're not stepping all over each other. And in terms of like a student doing research, it's become almost expected, I think, now that students will do research when they're an undergraduate if they're going to go on to grad school. I think it would be really difficult to get into grad school if you hadn't done some kind of undergraduate research in math. And so to have a project that then actually leads to a publication will do a lot of good to getting a student into graduate school.
But to you,
Well, it's not really clear what that means. You could ask these fine people over here what it means. I'm not really sure what that means. But my general rule of thumb is that it either counts or counts for half. So that's in my brain. If my brain was reality, that's what it would be. It would be that if it's a paper that I got published in a faculty research journal because I was doing a bunch of research and they did a piece, sure, of course that counts. But if it's sort of like it was mostly like a lower level project and we published it maybe in an undergraduate journal, I don't know, it counts a bit. I don't know.
and if they
That sounds
take
reasonable, at least.
your idea that you got them going on and then they go off and that's their field, then are you actually like competing?
Oh no.
No.
I don't think so. I would think we're more like I don't know. I feel maybe I'm really naive now that you're asking these questions. You made me worry, but I just kind of feel like
discipline. That's why
we know we're all big, one happy, collaborating family. I've never actually been in a competitive conflict with another mathematician like that.
My outside perspective
Thank
of
you.
mathematicians is they're very sharing, but I don't know if I didn't know if I was a mentor.
I believe that probably in the R1 research community at Princeton, things might be a bit more competitive.
Well, you showed a page from the archive, right? But
Yeah.
what people do now is as soon as they've got something, they post it on this website. It's freely available to everybody, and they don't wait for it to be accepted for publication. They post it there, and then they submit it somewhere. So it's very,
Math is very fast now.
Yeah. If you
Yeah.
were conniving under, you could possibly.
You could publish something false and put it on the archive.
You wouldn't get away with it. I mean, but-
No, it'd be ridiculous. It'd be a waste of time. We don't like to do
There are
that.
people who are banned from the archive.
Oh my goodness. Well, we shall not discuss those people.
Yeah, they do ban people who put up, false papers over and over again.
Oh.
Wow.
Oh,
Oh,
Because
well,
new hypothesis
yes.
is anytime.
Yeah, right.
I get emails about those kinds of papers. Cause sometimes there are nutty people.
Yeah, but they do eventually ban some.
Yeah. Yeah.
Could you comment on the relationship between knot theory and, say, chemistry or biology, just very impressionistically for...
I can say that there is a connection. But I can also say that I don't particularly care about that connection. Because, I just want to do like pure math, right? But I know you know that. So, but I know you're asking so that I can tell the students here about this connection. So I'm going to pretend I care about it just for a minute. So I think that I believe that various proteins and DNA and molecules and other biological chemistry stuff can be knotted up in different ways. And in fact, I know there is one thing that's interesting is that it actually matters whether knots are left-handed or right-handed when you're dealing with chemistry. So one of you out there has a trefoil knot. It's very simple. It just looks like a clover, right? It turns out, it turns out that this clover, which is the simplest possible knot, if we were to take the mirror image of this knot, we would not be able to stretch it around and get it back to this. So the mirror image of this knot and this knot are actually different. There's a left-handed trefoil and a right-handed trefoil, and mathematicians just we don't care. We're not going to think about that. But chemists would care about this a lot, and then that is something that comes out. Yeah.
Actually, mathematicians care about that.
Well, they do, but most of the time in knot theory, we just perpetrate the big lie, right? Like you don't find out till a lot later where you're like, oh, did you know there's two of these actually, not just one? And then like you've already been thinking about knot theory for a year,
Well, and some knots are equivalent to it.
Somewhat, yeah. So I don't remember if that's chiral or achiral or amphichiral, but it's chirality somehow, yeah. Yeah.
This might be another question where you have to pretend to care about something.
I'm good at that.
Okay. I don't know too, much at all about knots. This is an introduction for me, but I'm wondering, do they have are knots of real interest to people who are doing either applied mathematics or some type of computing science?
I don't know the answer to that question at all, but maybe Elizabeth does. She looks like she does. No?
I was just going to say this might be one of the cases where we actually refer a problem out. And you heard she's talking about taking powers of very large matrices. So that's the sort of thing where if your friendly computer scientist had some sort of fast way of doing things, you'd be really glad about it.
That's true. Or some, I know in computer science there's a lot of graphs, networks, trees type of thing, and some of that comes up sometimes in knot theory. I could imagine borrowing some of that from them. But I don't know what they would find useful about it.
But and as far as applications go, so molecular chirality is an area where knot theory is applied in chemistry. So you can imagine an applied mathematician who's working with chemists.
Mm-hmm. But I can't stress enough that pure mathematicians do whatever they want. They don't do something because it's useful. They just do it. It's like art. They do it because it's interesting, it's beautiful, they want to. That's what we do. So I'm sorry, I feel a little lost when you ask me how it's useful. It's like, how is this painting useful?
Oh, yeah.
How would a train engineer use your painting? But no, I like your question. I'm not trying to. Yeah.
I'm on the same.
Yeah.
But I was just curious.
Yeah. Actually, now I'm going to have to go find out because that's kind of interesting.
I'll give you one example.
Oh, okay.
Where you're dealing with different knots, things that knot up. Long strings, think of very long polymers, where they interact with each other and twist and braid up in different ways. How they do that, and are they essentially the same or not, leads to different densities and different properties of non-Newtonian fluid mechanics.
Wow. Oh, I'm so glad you said that.
So it is actually useful in those fields.
And also, the other reason I'm glad you said that is because Jason Cantarella, whose data this is, and they reminded me, he actually does something like this, where he has a terribly long strand that gets kind of randomly knotted, and then he has to determine the degree of knottingness, and that definitely has something to do with all those fancy things that you said. Yeah.
Following along that line, so DNA is also a long, skinny thing that knots itself up. And somehow it has been around long enough and cleverly organized itself enough that it will tend to knot itself to minimize the the cutting number?
Yeah.
If it wanted to untangle, it minimizes the number of times it has to break and rejoin it.
Okay, I lied because that is really cool. Because I do remember something about this. It is true what you said. I saw a talk about this once where the DNA gets all knotted and then there's something that comes and cuts it and then rejoins it again. And it's basically taking a strand that is overcrossing, cutting it and making it an undercrossing. And it turns out that whatever biological process does this is shockingly good at doing the right unknotting, the right crossing changes. So there have been, people study how many crossing changes does it take to change a knot into the unknot, right, into something that's not knotted at all. So if you could just swap all crossings like this to this, if you wanted to, how many would you have to do? And biology seems to have a leg up on us on this one, and they do it to really complicated ones, and nobody knows why. Yeah. Although I think that somebody suggested it might be because of the amount of bendiness, that it cuts where things are bendier, and that the bendiness itself is an indication of kind of the density, what happens. I'm now at the limit of my knowledge about biology. Yeah.
Is it generally known, Laura, if there's a fixed ratio between, say, the ratio between the thickness of a string and the length that you need for tying, different knots?
Well, I believe that when they do this rope length stuff, the tight knots, that you could either fix the tube and try to fix the width and make it as short as you want,
right,
or fix the length and make it as wide as you want, and that the two are equivalent problems.
Ah.
Yeah. So not only is there a ratio, I believe they're
right,
exactly equivalent. And in fact, these knots that I'm handing out, a lot of them had two different versions. Did you guys get to see the knots over there? Because they all came back. That's really nice. Oh, okay. Well, thank you for being so honest about Just kidding. You don't have. Okay. Anyway, I have two versions, a tight version and a loose version. And so it looks like I took the tight version and loosened it.
Right.
But really what I did is I made it bigger and I made the tube smaller.
I see it.
So it's the same. Yeah.
Well, my question, kind of answers like, you know, what I'm curious about is like thickness and length proportional to each other, or is it like thickness is proportional to length squared, or?
For a given knot?
Yeah.
I think
Or like,
for a
you know,
given
is it-
knot, it is actually that ratio of thickness to length that's determining what they would call the rope length or the tightness
I
of the
see.
knot itself, right?
I
So,
see.
and then that each knot will have its own kind of characteristic ratio like that. And so in my mind, I'm setting one of them to one or the other one to one, and it's not a ratio anymore.
I see.
Right?
I see. I see.
But, yeah.
Does anyone use maximum curvature or minimum curvature as a bound?
I don't know that. I don't know. But people do study curvature of knots, so there's sort of a more differential geometry type camp that studies knots that might think about that. Yeah.
So, I'm sorry if I didn't necessarily, did I understand correctly that it's not known if there are any knots which fail to be spiral?
Yeah. That would be awesome if we could find one of those. So, because, you know, it's hard to prove that all knots are spiral. That's not going to be fun. So I'm kind of hoping there's one that isn't spiral. But on the other hand, like if you're allowed to have as many repeats as you want and as many strands as you want, so you're like wildly inefficient,
Right.
I don't know. Maybe you could do it.
So in a way, that would be the best case, though, because then all of this work would be for all knots.
Yeah, except here's why I said that would be useless. So, okay, so we got excited at first thinking exactly that thing. We're like, oh, and if this was true for all knots, then we have determinant formula for all knots. But the procedure by which we would identify which spiral knot a given knot is more difficult than the procedure by which we would normally compute its determinant. So,
That's likely to be undecidable.
well, if it's the word problem, it is, but I don't think that is what it will
Well,
be.
no,
Well, maybe it will be the word problem.
the equivalence of knot rejection.
Well, if you're doing like that fundamental group of the knot complement thing, you really have the word problem where you're trying to figure out, you know, and that would do it. But I'm not sure because a lot of stuff has
That's
been
not the general
happening.
word problem.
No. But a lot, yeah. But a lot of stuff has been going on, and there's even things that are complete invariants, and I'm not really sure exactly.
Homomorphism type of the complement, for example, that's pretty recent result.
Yeah, well, there's even more. I mean, it's insane. The last 5 years have been crazy. Yeah. Thank goodness for the archive.
They're all as equally indistinguishable. I mean,
Right, and the better your invariant is at distinguishing knots, the more difficult it is to compute. So there's, you know, maybe, yeah. Yeah.
Okay, to put it mildly, I am not a mathematician.
Oh, we made it this far. It's almost been 45 minutes.
I know, well, someone had to burst the bubble. Being multidisciplinary and all. Can I see the picture of the knots themselves?
Yeah, sure, like the table?
Yeah, the first one with all the happy pictures, very much like the ones that the student did in
Oh, yeah, that
class
beautiful.
downstairs.
It'll take a minute, but I can get there.
It's kind of funny that soon the MakerBot will be recreating what the student made by the
Here
computer.
it is. So,
Right. So that thing in the front is these flat ones. So they made it 3D, but they're modeled after these exact pictures. This is like the knot table, right? And so on mine are going to be a lot more like I hope we can display them together. Can we do that?
So here's my question. This seems to be a series. And when I was introduced to it the last time I took the course, it was the number of crossings.
Mhm.
Now I understand there's many permutations of the various different. When we get
There's lots of six
six
crossing
in
knots.
the
That's right.
series, right? But it's a series. And so point, line, plane is kind of a series.
Mhm.
And sphere, triangle, cube is a
Mhm.
series. For a very long time, those forms have been used. I mean, there's a famous Zen painting, which is just a circle, and next to it a triangle, and
That's
next
cool.
to it a cube, a square.
Uh-huh.
And I'm still not quite clear why that was a Zen monk. But basically, he's sort of representing the nature of being
Mhm.
with those things. And so this seems like a more complex version of that kind of series. Which leads me to think that for a very long time those series were believed to be the building blocks of the world. And I understood very little of what you said.
Thank you.
As I was, not that I should, right? I mean, believe me, I
just teasing.
calculus, okay? So at this point, I am.
That's okay. I'm holding on with the Zen thing, and we'll get there.
So the question is, for a Zen monk and for believers, this underlying structure is there and divine, and that's the way it is. So when you look at your task of pure mathematics, is it a task of uncovering what you feel already exists?
Why did that fail? Sneaking Platonism.
And that would be that's the underlying question.
Now see,
Wait, what did I
I'm
miss?
just gonna leave the room and just explode. No, so that's my question.
Wait, is it a question? Wait, I didn't understand what was funny.
Is it a question?
Is mathematics invented or discovered?
The nature of what?
Is mathematics invented or discovered?
Oh, I don't care about that. I'm just kidding.
But I do.
I just
And I'm asking the
so
question.
it's a really good answer. Like it really just means I don't know the answer to that question.
Well, I figure so.
Well, I don't know. I mean, it's kind of both. I think math people are good at avoiding semantic issues, I think. So I just say we have both. Oh, I'm sorry.
Semantic.
We're good at resolving a problem by claiming the issue is semantic, is what I meant to say. So I'm going to call that. I mean, I think it's both. I wouldn't dare to say either, especially given the reaction that ensued.
He said, I think it's both. I wouldn't dare to see either.
Independently. Exclusively of the other. I don't know, math people. Who has an opinion? Are you going to fight? Yeah.
I have an argument for discovery.
Okay.
So consider the entire length of existence, and I don't know too much physics, so just excuse me if I'm simplifying things to just make the whole universe only four-dimensional. Then the whole universe.
I'm okay with that.
Yeah, I'm okay with that too. Yeah.
Then the whole universe is just this complex shape, and time is an illusion. And so, in the case where we were creating these things or inventing these things, they already existed in some sense, because it is just a shape, and we ourselves are just these shapes. So, in a way, we're discovering even when we're inventing, because we're just figuring out what happens at that t time. Or what the whole universe looks like what the shape is at that time. So it's always discovery, because you're figuring out what you were destined to do forever. You know what I mean? Like in a way, so the shape of where I'm going to be moving is already decided, because if the universe is just a four-dimensional object, then when I get up, I just discovered that I was going to stand at that time t. I didn't know it before. So in a sense, all things are discovery.
So this is like the argument between free will and determinism, you're saying?
Well, I don't think they're
because that's going to cause a fight.
That's
interesting. Yeah.
The tangentially relevant is mentioned that historically, actually not the problem of knot theory was posed because chemists thought that matter was going to turn out to be made of knots in the ether, and that's why they were interested. So they did think it was a fundamental building block question. They said, mathematicians, we need to understand knots get busy. And mathematicians were like, oh, this is cool, this is interesting. And then chemists were like, no, the ether's going to
Yeah, never mind. We don't want you to think about it anymore. And the mathematicians we still want to think about
now,
it.
100 years later, actually, they're like, oh, yes, but we did want to know about knots anyway. It's useful for something else.
Yeah.
So it's a nice interplay, actually, of applied problem, pure extension, applied return in a totally different context.
Oops, there wasn't really either.
There are entire departments of philosophy of science that argue this pretty much all the time.
Yeah, that would be an interesting place to work.
There are
Kind of a scary place to work. I don't know. To me, like some other people are afraid of mathematics. I'm afraid of that.
It's a fascinating field,
yeah.
and the historically it's been a case of as you go through the sciences, the idea that you can have a Kuhnian revolution and implying that what are we discovering, is it actually real that we're looking at? And so it was in the 1980s where a lot of, mostly psychologists, were turning it into, well, we've made everything else invented in the philosophy of science, how should math be any different? And the whole invented first discovered became very deep. A gentleman by the name of Philip Kitcher wrote the definitive book in about 1990 on mathematics is invented, not discovered. It was the really big one. And
So he settled the question.
And, well, he claimed it was invented. I spent 3 years learning enough philosophy to read that book to understand what its argument was, and decided it was completely bogus. Because his key argument was, you can't understand all of mathematics in one hit. How can you know that you're discovering stuff, whether you're inventing it due to the limitations of the brain? My short answer is, hasn't he ever heard of the lemma? Do a page, you cannot encompass all of concepts in your brain, but you can encompass enough for a one-page proof of mathematics, which becomes a one line that you can use later, and you can build the structure up. So his entire argument was great and completely wrong.
See, that's good. It's kind of like hoping that I show that one of these isn't spiral, because it's way easier to show that argument is not so good than this argument is the best argument.
He was on my PhD committee.
Wow.
But in music, so he was an outside member, so I have no opinion on whether he was right or wrong.
A lot of the rest of his work is fascinating, and I'm not denigrating it. It's just that one particular book was a real big deal when it came out.
Elizabeth had her hand up.
Without wanting to defend Kitchener or a psychological approach to mathematics in any way, so let me propose that we're moving from knowledge in which at least the connections are airtight to more of a dialectic discussion when we try to talk about philosophy and mathematics. And that there's at least a solid argument to be made that we've changed kind of discussion now. We're not talking about something that we're going to solve in the same way. And we're going to understand if 6.1 and 6.2 really happen to be different.
Except that you had to invent something. She's saying you have to invent things to figure that out. How that invention happens.
You're inventing ways of describing things. Languages are different, but they talk about the same thing within the context of what human beings are. There are certain things that, I don't care which way you describe a number, 13 has certain inherent qualities regardless of which way you do it.
So is 13 beautiful?
13?
Pick a reason.
Oh, you asked the right person. Yeah.
13 is beautiful because it's the base where Douglas Adams' joke in Hitchhiker's Guide to the Galaxy works.
Is it more beautiful than 12?
You have to define beautiful.
And there's your problem. You define beautiful. However, the primeness of 13 is well defined when you know what prime is. And why do you think prime is important? Because divisibility naturally occurs when you start dealing with natural numbers.
Wait, can I just say this is why in math these kinds of questions don't happen? Because like in order
you would like to have
in this question that you asked, you have to ask what is discoverable. Like what are we, if you want to know if math is discovery, you have to know what kinds of things are available for discovery and not. In math, when we do a problem, we know exactly the objects we're dealing with. There is no, we make up an object or we discover an object. I don't know which one, but we do one of those two things, right? And then we have an object, we do something with it, and these questions where, you know, where things are debatable, that'll happen to me. You know, like we don't have that kind of discussion. I mean, it's also good to have that kind of discussion, but I just think that that's interesting, like on a meta level. The discussion that we're having is a very non-mathematical discussion, which is really interesting.
Why we're having it here, baby.
Yeah, which is really cool. So anyway, I just wanted to point out this facet of mathematics that we do always start with a set of definitions. We don't argue about that. So, and when someone proves something, if you understand the proof and the methods are sound, that's the proof, you know. And you could argue that you want to work in this system or that system or whatever, but once you decide what you're working in, there is no argument.
The reason I brought that up is because as you were talking this through, I understood very, very, very little of it. But as you were showing the strands, all I could think was DNA, 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 DNA. And as we got to the end, someone said, and in fact, this is all about DNA. And I thought, well, I know, it's not all about DNA, but clearly there are relationships with DNA. And there are relationships with these other systems. And even not knowing a darn thing about what you were saying, somehow I started going in that direction. So the question is, why? Now I know that's not the
no, but that's really interesting. That really freaks me out, that kind of thing.
Well, maybe you could say we invented knots and then discovered that they actually existed.
Or maybe we discovered knots and then we invented a connection to DNA. I don't know, just making that up. I'm not arguing that. That's really interesting. Oh, yeah, Edwin.
I think culturally we're very schizophrenic in a certain sense because, you know, we're the queen of the sciences, right? You know, our discipline is the queen of the sciences. The sciences would not be possible without our discipline.
Who's the king?
There is
mathematics. Mathematics.
We're the queen.
Yeah, it's a popular reference anyway.
I don't know why, but it's true.
It's a popular reference to kind of, you know, I think it goes back to Gauss. So anyway, Gauss described mathematics as the queen of the sciences. But somehow, you know, when we kind of, like, you know, one of the great mysteries of our subjects is that people study things just because they're beautiful and they create or invent things just because they're really beautiful. For no good reason, and 100 years later it turns out to be extremely useful. You know, if you think of, like, you know, prime number factorization, for example, every time we run our credit cards or if we want to send codes or anything like that, we can't do it without prime number factorization, right? But nobody studied it for those reasons. Nobody had a credit card in mind or, you know, transformation of data in secret, etc. But the experience is that when we play this game of talking about our subject as being part of the sciences, it means, you know, we get more money for our students through grants because we're part of the sciences. We get all these people saying we're great because we're part of the sciences, right? And I think we kind of play along with that game as well, right?
We're the M in STEM.
We're the M in STEM, exactly, right? But then, right, you know, the flip side too, though, is that, like, when we think of, you know, to go back to how useful things are, you know, the remarkable thing about, you know, reading Shakespeare is that 500 years later, people still read it and see something that they're like, oh my goodness, I can't believe somebody thought this 500 years ago. And the experiences of engaging in mathematics are very similar to the experience of someone, you know, engaging, you know, in literature or any other creative purpose, including the sciences. But it's, you know, I don't think Shakespeare, you know, discovered, you know, Macbeth, you know. I think he created it, you know. But then, you know, we look at these knots and, you know, they come up in real life and, oh my, you know, we must have just, you know, discovered them rather than created it, you know.
Yeah. You know, bouncing off that, if I can, I think you were talking a little bit about how our society is really schizophrenic and how we approach things, and I think you touched on the issue of, like, why we're asking these questions of how this can be applied math, basically, when in a lot of aspects it's pure math. And I'm an artist, guys. I'm not a mathematician, so forgive me if I screw these terms up. But you also talked about how people don't do things necessarily because they're useful. They do them because they're attracted to them for whatever reason. They're beautiful or they're engaging or whatever. And later down the road, it turns out to be useful. And I think that's an example of when people do what they want and what they're passionate about, even if it's incredibly specialized, like whether that's art or math or, like, you constantly, I'm in the math and art class right now, and the mathematicians are constantly like, why are the artists painting one line on a canvas, like, with, like, paint made from chameleon ink or something? Like, incredibly specialized things that no one really cares about. And then on the flip side, the artists are like, why are mathematicians doing pure math? No one understands this. You can talk about this with 5 other people in the world. And I think the example of 100 years down the road it being useful kind of applies to that in a more abstract sense. When people do incredibly specialized things and do them passionately, it's not necessarily that it'll turn out to be useful 100 years down the road. I feel like that's just one of the positive consequences. And the other positive consequences are that people are doing things that expand their minds in their own field, and that has broader implications in a societal sense. If everyone were to do that, rather than to contribute to a system, you know, go to college, get married, get a job, not necessarily in that order, you know, how would our society be different if we weren't so focused on applied and useful? What would our society be like? That's what we do.
So
It might be a mess.
I'd just like to say that was very nicely articulated. For those of us in humanities and social sciences, that the questions increasingly become of what value does your field of study, what value does it provide to greater society that we're dead, right? Stanley Fish has been writing a lot about this in the last few years in the New York Times, and that is historically not been a question that has been asked at universities. And it shows really how schizophrenic we become, and it shows how universities have changed. Universities historically have been all about the life of the mind. And I'd argue that regardless of what discipline you're in, that's what we are supposed to pursue. We pursue discovery in all of our various disciplines because it speaks to the human condition in different ways, but it speaks to the human condition. If it has some usefulness and value, terrific. But I fear I do not want to devalue what you're doing because maybe it doesn't have any obvious applicability. Much of what I do may not have any obvious applicability. But I'd argue that that it nonetheless has some sort of core fundamental value to our students. If in no other way than in some sort of abstract way, like I said, it speaks to the life of the mind.
I definitely want to second that because I think I willfully ignore anything that my work could ever be used for that is productive. You know, like that's mortifying to me. Like maybe later, 100 years from now, that can happen, but that's not my goal. Like it doesn't validate what I did to suddenly have it be useful. In fact, it just, I don't want to think about it. You know, like that's not why I did it. I don't mind that it happens, but then the assumption is that, oh, now your work is useful because it has this useful thing. And it's I've given a lot of talks. I've never, ever given a talk where someone at the end didn't ask me how what I was talking about was useful, no matter what the subject. You know, they'll say, well, how is this useful? There's always that question, because everybody wants to know, right? It's not like they're challenging that it has to have utility. I think it's more just that they're curious, like, how do I place this in the context of the world? But then when it comes down to questions like funding, it's the peer side is not always the side that gets the funding. It's not really bad here, but when I was at Duke, there was a huge difference between the funding that the applied mathematicians got and the funding that the pure mathematicians got. You know, like, because they have all these huge grants and we have chalk. You know, it can get really stark.
But I think it's important. I mean, clearly, I agree with these sentiments. But there is something about there's a kind of ethical question in terms of individual versus collective, right? I mean, in other words, yes, wouldn't it be great? I mean, the counter argument would be, wouldn't it be great if absolutely everyone would do exactly what they wanted all the time? Great. If the answer,
I think that'd be crazy.
Well, then it's okay for you, but it's not okay for other people.
Well, other people do other things whatever they want.
Well, that's my point.
Like maybe art people do whatever they want.
But I'm saying there's a spectrum between the individual and the collective. Mm-hmm. And there's what benefits the individual, and there's what benefits the collective. And so, obviously, between those two poles, but when something comes up, it's not just, okay, what can we do with this? They're trying to figure out, okay, how does that have to do with us rather than you?
That's right, or just math. They wanted to extend outside of math. And that's natural. I understand that.
Well, it comes down to the fact that there's more math now than there was. Short answer. If you go back to 1900, it was possible to know pretty much all of science. And now it isn't. And there's the requirement of speciality because of that. The concept of applied versus pure mathematics as different disciplines dates from World War II. And wasn't around before that. And the concept, you weren't a mathematician, you were a natural philosopher until 1800, 1850? You're going to disagree with me?
Well, in a recorded sense. Well, actually, I want to go back and disagree with David 2 steps earlier. So, I take your point. On the other hand, I think the contrast between what is pure and applied, or what is useful and not, is to some extent a false dichotomy. And I just want to say that anybody who wonders about the utility of English departments is welcome to come read some of the email that I routinely get. And then they will see that there is a real distinction between people who read and write with attention, with respect, with the language. And I'm not talking punctuation here. And people who don't. Or anybody who's ever tried to find their way through a VCR setup manual. You know that their technical writing matters, right? And that it turns on what? Use of language. Or anybody who's ever had to listen to a super naive political argument. Okay? Will know that it would sure be nice if one's neighbor or one's in-laws had taken some political theory courses and could at least have a somewhat more nuanced appreciation of the problem. So I would say that there's a really easy argument that all of the humanities and social sciences are tremendously useful.
Well, another argument that John Stuart Mill would give, and that is someone sits here, may not be able to follow a thing that's going on, but discerns in Laura's presentation, right, an intense passion for what she does, a love for it, right, and may glean from that, right, a desire, a will to follow his or her own passion, to follow his or her own path, to do what really sort of lights their fire, right? And Mill would argue, right, to live in a world like that, right, where we see people pursuing, right, their passions makes life itself more beautiful, more worth living, right? That's what Mill wants. He wants a society that is diverse and, he would say, rich and robust in that way, right? So it has a certain sort of real, almost spiritualness to it. And I would argue, I would argue that you could claim that that has utilitarian value.
I mean, there is actual concrete utilitarian value in people being happy. They are more productive and they contribute to things in a more positive way.
Well, and just to clarify, I'm not saying no math should be useful. I'm saying that I would rather fight for the right to have some math not be useful. And so then when my math does become useful for something, I don't want to hear about that, because then that diminishes the fight for some math to not be useful, because that's the corner that I live in.
Would you do a math project that was motivated by the real world?
Oh, of course I would. You and I have worked together.
And that completely blows.
But I like to have some things that I do because I do.
And every applied mathematician, scientist,
yeah, you're doing it because it's what you want to do. It just happens to be.
However, your typical applied mathematician isn't doing it because that's where the research funding is. They're doing it because they're interested in it.
Right. Oh no, that's definitely true. And I've collaborated with a bunch of applied mathematicians. Actually, I really like doing that because we talk kind of really differently.
I think we had time for maybe 2 more questions, and then.
What's the most beautiful knot?
And why? I will tell you why. I decided why. It's 7-7 because I hate how it looks right here. I don't like that at all. It's too symmetrical. I don't even like the shape that it makes. And so I asked my son, who's 8, what knot do you want me to print next? And he looked at this table and he said 7-7. I said, oh honey, no, not 7-7. That's not the knot that I like. And he said, no, I like that because my favorite number is 7. So then I printed it, and after printing it, it's the first knot that I felt looked really different after I printed it than what it looks like on the screen, and it's beautiful. So it's like the ugly duckling of knots to me. So I was just so happy. I'm like, I don't want to print that. It's so ugly. And for the first time, a knot came out where I'm like, I actually see structure in this knot that's not in this picture, you know. So it changed my mind. So today, that's my favorite knot. That's my most favorite.
It seems like we've been arguing back and forth about applied versus pure and the idea of usefulness. And it seems to be very short-sighted to look at an experiment or a body of work before it started or when it's in its beginnings and to say, well, that doesn't look like it has any application, so it will never be useful. It's something we shouldn't pursue. We close ourselves off to the fact that 100 years down the road, it could have a practical application, and if we never pursued all those avenues of just something we're passionate about or something that seems intriguing, that's a whole area of exploration that's completely dark and that could have been useful at some other place at some other time. So it seems very short-sighted to me.
I think that's how.
That is our utility, I guess, yeah.
It's just through people experimenting, and then years and years down the line, they realize, oh, with this, we can do this.
Our non-utility has a utility.
Let's thank Laura one more time.